All right, ladies and gentlemen, welcome back to another video with Mr. Kenton for AP Chemistry. We're moving through Unit 6, which is on thermochemistry, and we're now into topic 6.4. And so in our Brown and LeMay textbook, this is going to be section 5.5, and we're going to be looking at heat capacity and calorimetry. And so all of the things we've been looking at thus far have been talking about kind of conceptually how we can identify and determine heat, thermal energy, things like that. But now we're going to look at a specific quantity of substances, their heat capacity, and we're going to look at a technique, calorimetry, which is going to allow us to actually calculate the Q value for a given process. Okay, now we're going to start by looking at substances where you're simply heating up an object using calorimetry, but we're going to be able to expand that later to our chemical reactions. So thanks for joining me. Let's go ahead and dive right in here. So Q, as we've already defined, is the quantity of heat transfer. It is heat, right? This is the quantity of heat that's being transferred, so it's measured in joules. Now there are three factors that are going to contribute to the amount of heat that's being transferred. And those three factors are mass, the specific heat capacity, and the change in temperature. Now, for each of these factors, it's important to understand just from a units perspective what we're dealing with. So mass in this particular case is going to be measured in grams, right? Your specific heat capacity, this is going to be a measure of the substance's properties that tells you something about how much energy is required to raise that object's temperature, right? And so in terms of a substance's heat capacity, it's generally joules per gram Kelvin, something like that, or joules per gram Celsius, something like that. So this is typically joules per gram degrees Celsius or joules per gram Kelvin. And then the change in temperature, right? T final minus T initial. You could see this as degrees Celsius or in Kelvin. And the nice thing is when we're talking about changes in temperature, a change in Kelvin and a change in degrees Celsius, they're actually the same exact value. So that's kind of a nice piece. And it gets us this particular equation right here. Q equals MC delta T. So the mass times the specific heat capacity times the change in temperature, and that's how we're going to find Q. And remember, Q is going to be measured in joules or kilojoules, depending on what you're dealing with, right? You could make that conversion if you needed to at the end. So that's how we're going to be able to quantitatively determine the heat transfer. Now, let's talk about this idea of specific heat capacity and heat capacity, because they are different, but they are useful. So specific heat capacity or specific heat is the amount of energy required to raise the temperature of 1 gram of a substance by 1 Kelvin. Now, the biggest piece that is important here when making the distinction between specific heat capacity and heat capacity is this piece right here, right? There is a specific amount of substance that we're raising the temperature by. It's simply 1 gram of a substance. All right. And so the units for specific heat capacity, like we saw in the previous slide, are joules per gram degrees Celsius. And some things to note, water, for example, has a relatively high specific heat, meaning it takes more energy to raise its temperature than other substances. While our metals tend to have lower specific heats, meaning as energy is added to a metal, it tends to raise its temperature much more quickly. It requires less energy to do so. Now, specific heat capacity is an intensive property. It doesn't matter how much of each substance you have. It's just going to be a property that stays consistent, right? Thinking about like density, for example. The density of water is 1 gram per milliliter. It doesn't matter if you have 5 grams or 5,000 grams of water. The density of water is still 1 gram per milliliter. The same thing is true of specific heat. It doesn't matter if you have 5 grams of a substance or 5,000 grams of that substance. The specific heat capacity for that individual substance is constant. Now that leads us into heat capacity. Now heat capacity can look at quantities that are beyond simply 1 gram. So heat capacity is the amount of energy required to raise the temperature of a substance by 1 Kelvin. Now, typically, we're dealing with 1 mole of a substance. It could be for any quantity of that substance, but the heat capacity is just looking at the overall energy capacity needed for that whole substance. The units here are in joules per degree Celsius, and heat capacity is an extensive property. And again, we've seen that term extensive mean it's quantity dependent, right? Again, we talked about how specific heat would be something that doesn't change, but the amount of energy needed to raise the temperature of 5 grams of water is certainly going to be very different than the energy required to raise the temperature of, let's say, 5,000 grams of water, right? And so that heat capacity, that's something that is extensive. Our specific heat capacity is not. Okay, so I hope that makes sense in terms of the differences between those two things, that they're related, but there's a slight difference. Now, the unique thing about specific heat capacities is that each substance has its own unique specific heat. Now, don't worry about trying to memorize a bunch of specific heat values. Those will typically be provided to you in a table or within a problem that you're dealing with. Now, like I was alluding to on the previous slide, the higher the value for the specific heat, what that means is it's going to experience a smaller temperature change if you're adding the same amount of heat to a variety of substances, right? So obviously, the higher the specific heat, the smaller change in temperature that object's going to experience, right? Low specific heats mean that an object can experience greater temperature changes because each amount of energy that's being added is able to raise the temperature much more effective or much more during that change. And so you can see here, there's just a list of specific heats. You've got nitrogen, for example, 1.04. So that means that for every 1.04 joules of heat you add to a gram of nitrogen, you can raise its temperature by 1 degree. For aluminum, 0.9 joules, raise its temperature by 1 degree. For iron, 0.45 joules. For mercury, 0.14 joules. But then you look at something like water, 4.18 joules, right? So that's a pretty big difference, right? So essentially what we're saying here is mercury, you add the same amount of energy to mercury as you would water, mercury is going to undergo a significantly higher temperature change than the water. The other thing that you might see are molar heat capacities. And again, a molar heat capacity be the energy required to raise the temperature of a substance, 1 mole of a substance by 1 degree Celsius. And as always, check your units. Like a lot of chemistry problems can be fixed if we just simply check our units. So notice that in molar heat capacity, it's joules per mole Kelvin. All right. Now heat Q, as we've said, it's a form of energy that flows between 2 samples of matter that are at different temperatures. We've seen units of joules and calories. However, for us, context of AP, we're going to be looking at joules a lot more. But here, this just simply shows you all the ways that you can move between the different types of units. We've got 4.184 joules equals a calorie. Little c calorie, 1,000 little c calories is one big calorie. 1,000 calories is 1 kilocalorie. And then 1,000 joules is 1 kilojoule. All right. And with regards to this formula that we introduced towards the beginning of this particular video, Q equals mc delta T has a very specific application. It can be used when there is a temperature change, right? Notice that it's delta T, right? So we're going to use this expression when an object is experiencing a change in its temperature. If it doesn't experience a change in temperature, there is a way that we can calculate the heat that's being added or lost by that particular substance, but it's going to look a little bit different. All right, now this leads us into calorimetry. So this is the actual experimental setup that's going to allow us to calculate Q. Now, going back to enthalpy for a second, We can't know the exact enthalpy of the reactants and products, kind of like our internal energy problem, where we couldn't know the internal energy initial and final, but we could know the change in it. Delta H is determined through calorimetry, and it's a measurement of the heat flow. And so in order to do that, we use an instrument called a calorimeter. Now, our goal in calorimeters is to make sure that we're dealing with an isolated system. And if you think back to the terminology we looked at, an isolated system is one that does not allow heat transfer to occur between the system and the surroundings, and it doesn't allow for mass to be transferred from the surroundings in the system. So you're keeping everything within your system. That's why it's isolated. Now, for us, we can use something as simple as a coffee cup calorimeter, and it's going to have this particular setup. You got multiple coffee cups that are made of styrofoam. And then let's say you've got your reaction mixture in a solution. You've got a cork stopper that you're going to put on top of it so that the mass can't escape. You've got your glass stirrer that you can use to distribute and allow the solution to mix properly. And then you've got a way for a thermometer to be inserted so that you can measure temperature changes, right? And so this is a very, very cheap, I don't want to say super effective, but it's a somewhat effective isolated system that we can use to measure energy changes. Now, in a typical experiment, you use a calorimeter. What you do is, and this is in the context of just looking at substances. Maybe you have an unknown metal that's heated to a known temperature. For example, you put it in a water bath where the water's boiling, so you're heating up your metal to 100 degrees Celsius. And then what you do is you place it in a calorimeter that's got much colder water. And so essentially what happens, once that piece of metal is dropped into your calorimeter, the water around it is going to be heated up. Now the glass stirrer is there to help distribute it, but the heat gets transferred from the metal to the water until you reach thermal equilibrium. And remember, the hot particles of the metal are going to interact with the cold particles of the water, and energy is going to start leaving from the metal, moving into the water. And our goal here is we want all of the heat from the metal to go into the water. That's why we're using the coffee cups, trying to have an isolated system. And so then the heat gained by the water will be equal to the heat lost by the metal. So then you've got this particular equation, Q metal equals negative Q water. I think it actually should be reversed. It should be negative Q metal because the metal is what's losing heat, and the water is the substance that's gaining it, right? And so then you would have the mass of the metal times the specific heat of the metal times the change in temperature of the metal is going to equal to the mass of the water times the specific heat of the water times the change in temperature of the water. Okay, now keep in mind that the final temperature for both the metal and the water should be the same because they're going to reach thermal equilibrium. So the final temperature should be the same, but the change in temperature won't necessarily be the same. And you can use that relationship to determine how much heat was being transferred, right? So really useful experiment, really useful way to measure energy changes. And again, what the styrofoam cups are going to do, they're going to insulate the water and the metal so that any heat that's being transferred, instead of leaving and going directly into the surroundings, the styrofoam cup's going to capture that, keep it in so that the water continues to gain that energy rather than the surroundings. Now, there's another form of calorimetry known as bomb calorimetry. And so those happen in what's known as a sealed container, a lot more secure in a sense than our coffee cup calorimetry, but it's referred to as a bomb. Now, it's not actually a bomb. Nothing's going to blow up. But what happens is the heat gets absorbed or released, depending on what's going on, by the water, becomes a very good approximation of the enthalpy change for the overall reaction. Again, you've got a lot of very similar pieces. You've got a stirrer, you've got a place where the thermometer can fit in. You've got your reaction chamber where the process can take place. And then you've got your ignition wires that you can use to cause this process to take place. Now for a bomb calorimeter, which I'm fairly confident you won't have any bomb calorimetry problems on your AP exam, but Q reaction equals negative C cal times delta T, where negative C is the specific heat of your calorimeter. Now, in bomb calorimetry, the volume in the bomb calorimetry is constant. And so what's measured is really the change in internal energy, not enthalpy. However, when you really start to look at this, the difference is pretty small. All right, so let's take a look at an example. So let's say you had almonds and cashews that were burned in a bomb calorimeter that contained water, and the following data was collected. So we got our data table there, and we want to know what was the heat gained by the water for each nut. So, we've got our massive calorimeter water, massive water in the calorimeter. We got the specific heat of the water. We got the initial and final temperatures of the water. So we can use that. We can say, all right, so we're going to have Q1. We're going to do it based on the almond. So I'm going to say QA. And so then it's going to be mass. So that 2,000 milliliters, don't forget, 1 gram per milliliter equals the density of water. So that means that 1 gram is equal to 1 milliliter for water. So that means that we've got 2,000 grams of water times the specific heat, 4.18 joules per gram degrees Celsius, times delta T. Now our final temperature was 40.5 and our initial temperature was 22.5. Okay. I probably shouldn't say that this is QA, this is QW. It's the Q of the water for the first experiment. We'll say it's the first experiment. So we'll say QW1. All right. So you got 2,000 times 4.18 times 40.5 minus 22.5. And so looking at this, we need 3 significant digits in our answer. And so we're going to have that Q1 here, QW1 equals, let's see here again, to 2 significant digits. I'm going to have 1.5 times 10 to the 1, 2, 3, 4, 5, 10 to the 5th joules of energy that was gained by the water. Okay. And to do the second part for the energy that was gained by the water from the burning of the cashew, very similar setup. It's going to be call this QW2, is going to equal to 1,000 grams times 4.18 joules per gram degrees Celsius times our final temperature, 51.3 minus 22.5. Okay, so we got 1,000 times 4.18 times 51.3 minus 22.5. And we've got QW2 equals 1.2 times 10 to the 5th joules. So that's how much energy was gained by the water. Okay. So it'd be the heat gained by the water in each of those scenarios. Hopefully that makes sense, and feel free to pause this, to rewind, whatever you need to do to make sure you got it. Now, the other thing they ask us here is they say, calculate the energy for each nut, and then which provides more energy per gram. Well, in order to figure out the energy per gram of the nut, we've already got the energy that was absorbed by the water. We can simply take both of those energies and divide it by the mass of the nut. So for the almond, so QA is going to simply equal 1.5 times 10 to the 5th divided by the mass of it, which was 6.0 grams, which this is going to get us our energy per gram. So we got 1.5 e to the 5th divided by 6. So then we've got roughly, we're going to have 2.5 times 10 to the 4th. This is going to be joules per gram for the almond. And then QC for the cashew, 1.2 e to the 5th divided by 5. And we've got 2.4 times 10 to the 4th joules per gram. Now, it's actually really close, but what we can see here is that the almond provides more energy per gram. Okay. All right. So hopefully that makes sense. And again, we simply took the energy that we calculated in the first part, divided by the mass of the almond and cashew respectively, and that gave us our overall, or our energy per gram. And you might think about, why did that work out? But think about it. The almond was in twice as much water, and it released almost the same amount of energy. So if there had been the same amount of water, it probably would have been much more noticeable here. But so you get 2.5 times 10 to the fourth joules per gram. All right. So hopefully that makes sense. Thank you guys for tuning in with me. Hope this was insightful. Please let me know if you have any questions, and I look forward to seeing you guys again soon. Take care.